When microbial mats first appeared, Earth was nothing like the world we see today. The sun was significantly dimmer, supplying barely 70% of its present luminosity, yet the planet was not frozen. Volcanic activity and a thick greenhouse atmosphere kept surface temperatures high, often exceeding levels tolerable for modern life. Days were short, lasting only 10 to 12 hours, because Earth's rotation was faster. The air was toxic, filled with methane, hydrogen sulfide, carbon dioxide, and ammonia, with almost no oxygen to buffer ultraviolet radiation. Oceans were acidic and saturated with dissolved iron and sulfur, producing a chemistry far removed from anything organisms experience today. In these unstable, high-energy conditions, microbial mats emerged along coastlines and volcanic shallows as dense, layered communities where bacteria and archaea formed the first stable ecosystems on the planet. Each layer performed a specialized metabolic function. Sulfur reducers generated hydrogen sulfide, phototrophs in the illuminated surface oxidized it, iron oxidizers captured electrons from ferrous minerals, and methanogens recycled waste products back into the network. This tight metabolic web allowed life to survive far from hydrothermal vents for the first time, but the cooperation was delicate. The mats depended entirely on a steady input of reduced compounds leaking from the crust. And as they spread into clearer, shallower waters, these donors became scarce. Sunlight was abundant, but usable chemical fuel was limited, creating structural tension between fast-growing surface phototrophs and deeper anaerobes that depended on their metabolites. Even faint traces of oxygen produced by primitive photochemical pathways damaged the iron-sulfur proteins of anaerobic partners, gradually destabilizing ancient symbiotic links. Selection began favoring cells that could expand their membranes, capture more light, and reduce their dependence on metabolic partners. Step by step, some lineages drifted toward autonomous photochemistry, duplicating reaction centers, strengthening redox control, and experimenting with more aggressive electron extraction. These pressures transformed microbial mats into evolutionary crucibles, where scarcity, sunlight, and chemical instability pushed certain phototrophs toward unprecedented innovations. From these tense ecological landscapes emerged the ancestors of Cyanobacteria, an organisms no longer constrained by the crust-bound chemistry that had powered life since the beginning. Microbial mats thus represent the first moment when biology began shifting from Earth's internal energy to the energy of the sky, setting the stage for the greatest metabolic revolution in the history of life.